Any questions at all about this class? I know it's probably not really on your mind because you're in the 24-hour Connects exam period, but any questions at all about how this class has been going? Concepts that we should reinforce, stuff like that?
Yeah, I actually have a question about the basal function.
Yeah, can you turn your video on?
Oh, sure. Um, so are we supposed to know what they are exactly?
Are you supposed to know what?
Or basal functions are exactly like how you derive them and what they look like, how to like write out the expression as a sum of.
You should know how to use them. Yeah. And I don't really want you guys to be going too much on the internet, but feel free to like print the Wikipedia article on Bessel functions as a PDF if you feel like that'll be helpful to you on an exam. The extent that you need to know them is basically what you will see on homework 5. In general, my philosophy in the class, I'm not going to put anything on the exam that you haven't had a chance to practice on homework on so far. So.
Okay.
Mm-hmm.
Could you elaborate a little bit more on what's the connection between J0, J1, J2, like what they are exactly?
They're just different. They're literally just different functions. They're like sines and cosines and stuff like that.
Okay.
It'd be like if you asked me how to elaborate between what's the relation between sine and cosine and stuff like that, then I would tell you just the various properties that I talked about. What if you plot them, what they look like. One is the derivative of the other. Stuff like that.
Okay.
So basically what the properties are. But as I mentioned in class on Monday, like, if you came from a different planet where you never saw a circle or a triangle, then you would also be really confused about sines and cosines.
Okay, cool. Thank you.
Yeah. Bessel functions are just the solution to that particular differential equation. In the same way that you can think about, you could one perfectly valid definition of sine and cosine is solutions to the equation dx or like dy squared dx squared plus y equals 0, right? You could define sine and cosine as, that way as well, and they would be equally valid as the way we typically define sines and cosines in terms of circles and triangles. So, okay. Any other questions? There will be plenty of time for questions as well after class, because my office hours is going to be right after class. As I mentioned on Friday, I'm going to do one more FFT example, but we at this point have moved on from FFT, and so today I'm going to talk, during the main lecture, I'm going to talk about something a little bit different. This is beyond the material for homework 5 and the exam now, by the way. Okay, and so this is where we have been so far in terms of FFT. The FFT basically allowed us to solve differential equations that look like this. We've had a few other solution methods. We talked about similarity solution and stuff as well to deal with that, right? But just in general, the philosophy is that partial differential equations are difficult to solve, and so therefore we need different solution methods to do that. And most of those solution methods involve reducing the PDE down to an ODE. Okay, hold on, let me do something real quick. Okay, and so once we reduce the PDE down to an ODE, then we can solve, right? And so that sort of becomes the game. And so in FFT, the way that we do that is, as I mentioned, there's these 4 steps. That first step is sort of the key step, is that we define our solution in terms of a sum of basis functions. And then the game becomes solving for the coefficients from the basis function. And it turns out that the equation that you solve for those coefficients is an ordinary differential equation that you can then solve, right? So today I'm going to talk about just a slightly different type of problem. It's actually the same differential equation as what we've always been doing, but the solution looks a little bit different because the problem is formulated slightly differently. So we've talked earlier about Stokes' first problem. Today what we're going to talk about is another famous problem called Stokes' second problem. Okay. Stokes' first problem, just to remind everyone, was we had a plate with some fluid above it. Let's give ourselves some axes real quick, x and the y. And if you recall, in Stokes' first problem, as y goes to infinity, we have some sort of fluid at rest. And then in Stokes' first problem, at time t equals 0, this plate is pulled to the right at some speed u suddenly. Okay. Stokes' second problem looks very similar, except now this plate on the bottom is oscillating. with some frequency omega. Okay. And basically, it's the same question. What is the flow profile look like in our fluid here? Okay. And so the analysis, at least in terms of how to frame this picture, these equations stuff looks pretty similar. The PDE is basically what you get if you were to reduce the Navier-Stokes equation down. Like that. Okay, and then we have a few boundary conditions, right? So again, for every derivative, you have to have one boundary condition. So the no-slip boundary condition in this case, that we'll call BC1, gives us that Vx is equal to u cosine omega t at y equals 0. Okay, and then of course we have another boundary condition, and that's that Vx is equal to 0 as y goes to infinity. Okay, that's it actually. This is the one sort of exception that we have where every derivative has to have a boundary condition. There actually is a time boundary condition. You can imagine that maybe at time t equals 0, the fluid is at rest or something like that. But that actually makes the solution overly complicated. So when I say an initial condition, I'll say none because we care about the long time solution. Here's what I mean. You know, you could imagine that if you let this thing go for a really long time, then eventually it'll start to oscillate and it won't really matter what the initial condition is, right? Even if everything started with a fluid at rest, if you have this plate that's sort of moving back and forth repeatedly, it won't really matter whether the fluid was at rest or was moving in some other direction or whatnot. Eventually, everything's just going to look sinusoidal anyway, right? And so the initial condition isn't really going to matter. Okay. So, anyone have any idea how we would solve this sort of problem? Just curious. I expect that the answer will be no, but I'm curious to just take any sort of suggestions or constructive feedback or whatever.
Like your solution is gonna be like some complex valued basis function, right? So you're gonna have to take the real part of that because you have a periodic.
Something like that, but we've sort of been doing that already anyway, and I'll get to what I mean when I say that. But maybe we can take something that Nikhil said and a little bit, not completely literally, but you know, Nikhil's the implicit assumption behind what Nikhil was saying is something about basis functions, right? And it makes a lot of sense, right? We've been talking a lot about basis functions and stuff, and so maybe we need to express our, just like in an FFT solution, we need to express our solution as a sum of different basis functions and stuff like that, right? So FFT stands for finite Fourier transform. The reason why it's called finite is because the domain is finite. And so that means that we have a finitely defined, or I guess basis functions, a finite number of basis functions that extend out to infinity, but they're not like continuous. They're discrete individual basis functions where n equals 1, n equals 2, n equals 3, n equals 4, and stuff like that. Not n equals 1/2, not n equals 1.5, not n equals 3.1415, etc. Okay. What we're going to talk about today are not FFT, but FT, Fourier transforms. Okay. And I'll just say that these oscillating problems with a poorly defined boundary condition are good for Fourier transforms. Okay. I will say that we don't have to necessarily use Fourier transforms in this class. In previous incarnations of this class years ago and stuff like that, Stokes' second problem is sort of something that most people in the graduate level fluids should know how to do, or can say that they've seen this problem before. Another way of solving this problem is to do something like assume that the solution is some sort of like can be expressed as some sort of oscillating solution, and then basically trying to find coefficients in something similar to what we've been doing in FFT. But that gets like really algebra really, really quickly, really, really hairy, and I don't really enjoy large amounts of algebra, and that doesn't really tell you much about what's physically going on. And so instead, we're going to talk about Fourier transforms. Okay, let me draw an analogy to FFT. Okay, so in FFT, we expressed the solution as a sum of basis functions. Okay, let me remind you what I mean when I say that. We would think about f of x. So before we would commonly have like f of vx of y and t, right? Or f of x, f of y and t, or something like that. The t is sort of, it doesn't really matter, right? Like every coefficient is a function of time, but you know, the t is sort of a separate thing, right? We're talking about our transform in terms of x. And so we could think about this as like a sum from n equals 1 to infinity of some coefficient times our basis function. And as I was talking about, you know, well, so here's our basis function right here, square root of 2 sine n pi x, right? And our coefficient here can be a function of time that then allows our f to be a function of x and t and stuff like that. But the transform is over the variable x, right? And then as a result, we can apply orthogonality and stuff like that and figure out what our coefficients here would be. This was the whole inner product idea and stuff like that, right? If you take an inner product of the function itself and the basis function, then you can recover the coefficients. And then the game becomes everything that we care about now has to do with actually finding these coefficients, right? So what I'll say is basically the Fourier transform is basically the same as FFT, except it's what happens when n now becomes continuous. Okay. So Fourier transform is FFT when n becomes continuous. Okay, and typically we don't write our basis functions in terms of sine n pi x. You can, but there's a much more general form of writing this. We typically write our basis functions using complex exponentials. Using complex exponentials. Okay, so nod your head if you've played with complex numbers before or you know what a complex number is. Now keep nodding your head if you've done calculus when it comes to complex numbers, complex analysis and stuff like that. Okay, cool. So fewer of you, right? That's good. Here we're actually not going to do too much calculus when we're using complex numbers, complex analysis, but we will get into that a little bit later on in this class. But for now, we're just going to, you know, use what I is. I is the square root of -1, right? That allows us to write kind of cool relationships like this. Okay. This is the polar representation of a complex number. If any of you guys are familiar with something like this, basically, it says that instead of thinking about a complex number in terms of a real part and an imaginary part, you can instead think about it in terms of like an angle. Like if you plot the complex number on like a real axis, you can think about it in terms of an angle. How many of you guys have seen this relationship before? Cool. So if you guys believe me, then what this means is that complex exponentials are sinusoidal. So what that means is that in Fourier transforms, just like how we've done in FFT, we can express our function as a sum, although now we're dealing with continuous things, and so we're talking about an integral by convention, we have something like 1 over 2 pi in the front. I'll get to that in a second. Times that. So our basis functions are now e to the ix, e to the ikx, just like how we were talking about sine of n pi y, or sine of n pi x. Okay. Now it's k times x, and it's e to the I times that. That gives us our sinusoids. Okay. And so our coefficients are f of k, like this, and we integrate now. Okay. And so just like how c of c sub n is a bunch of discrete coefficients, well, now we're talking about an actual function, and so that's why we call it a transform, because we're transforming now our entire like our function f of x into big F of k. And the 1 over 2 pi is just a random convention. Other people like to put the 1 over 2 pi in different places or something like that. For the rest of this class, we'll use something like this. Okay. Likewise, we can use something that's kind of like orthogonality, although not exactly. It's basically an inverse transform to recover what our coefficients would be if we know what the original function was. Okay, see how this guy right here looks very similar to this. Okay. The nice thing about Fourier transforms is that people already know a lot about how Fourier transforms actually work. Okay, so common functions actually already have Fourier transforms. You can look them up in a table. Okay, here's the definition of Fourier transforms as we talked about, that as we wrote down in the notes right here, right? Any function can be written in terms of a Fourier, this f of k is called the Fourier transform of this function, okay? And so you can recover the original function given its Fourier transform by applying this operation. Likewise, you can also calculate the Fourier transform of a function using this operation like this, as we already wrote down in the notes. But given this, there are all sorts of other functions that are already out there. For instance, let's say you have an exponential or something like that, or let's say you have a cosine or a sine or something like that. You can immediately calculate what the Fourier transform of that function is going to be just by looking it up in a table. Okay, and in Mathematica, it basically has these tables already like entered. And so if you were to type in Fourier transform or something, then it'll just give you the actual number. It'll actually just give you the values of the function here. Okay. The Fourier transform is linear, for instance. That's what this means. If you multiply a function by some value, then it just multiplies all the coefficients, or it multiplies the transform by that. If you were to shift the function, then it does something like this to it. We'll use some of these a little bit throughout the class or throughout this lecture. Kind of cool things about Fourier transforms. If you want to take the Fourier transform of a derivative, then there's also a way of expressing that. And it turns out that that instead of taking a derivative of the function here, you do like you just multiply it by ik in the front. We'll use that in a little bit in this class as well. Some things that you might see in some of these Fourier transforms is if you try and take the Fourier transform of 1, you get this delta function here. This delta here is basically the same thing as a Kronecker delta, except in real space, it's continuous. Okay, just like how the Kronecker delta function says that like delta mn is equal to 1 if m equals n and is equal to 0 elsewhere. This delta function basically says that it's equal to infinity if x is equal to 0 and is 0 for anything else. Okay, so it basically just says it's analogous to a Kronecker delta. It's what you would get if you were to take the Kronecker delta and make it continuous. Okay. The one other constraint, this function doesn't actually make any sense, though. You can see it's highly discontinuous, and you can't have infinity values in your function and stuff like that. And so one other constraint for the function is that when you take the integral from negative infinity to infinity, you always get 1 in the delta function. Just like in the Kronecker delta, you know how when you do a sum of something over a Kronecker delta, you can switch the indices and stuff like that, right? This is kind of analogous to that right here, right? If I were to take a sum of something and a Kronecker delta, this term right here, delta x minus a, would be something like in the Kronecker delta, it would look something like delta x a. Then I can do a sifting property and sift out only one value. Just like how in the Kronecker delta, you know, you can do the sum and only one of the values of that sum is something non-zero. And so then you can pick out that one value, right? That's essentially what this is as well. Okay. So given this, we can now actually just do a solution to this problem. Okay, you guys are still seeing what I'm seeing, right? This is the actual notes that I'm showing. Excellent. Okay, and so now we can do our 4-step method for success in terms of FFT, except now doing it to Fourier transforms. Okay, so step 1 was expressed in terms of basis functions, right? Solution. Okay, in Fourier transforms, we don't actually have to do that. This is already done. We just did that. It's always the same every single time. Okay, it's just we're talking about a Fourier transform or the inverse Fourier transform. So then the next step is to basically transform the PDE. Okay, there is some choice in Fourier transforms in terms of what variable to do a transform over. In the example that I'll talk about during office hours, and I think one of the homework problems, there is also there's a case there too where you could potentially transform either one of the two variables. In this case, the thing that's actually oscillating is the time variable, and so it might make sense to transform in terms of time instead of space. Okay, so what I mean is we're going to let f of yk be defined as the Fourier transform of the solution that we care about, v of yt. Okay. If we do that, then the PDE becomes this. Becomes this. Okay, so here's our original PDE. Here's our original PDE. We have dvx dt. And so we can go into our table of Fourier transforms and look at the derivative of the Fourier transform of a derivative. And as I mentioned, if I take a derivative of a function, then the Fourier transform is just ik to the power of that derivative. So in this case, n equals 1 times f of k. Okay, so that implies then that the PDE is ik times f of yk. Now the right-hand side is just this. So the nu is just a constant. And this derivative is actually, it's a derivative in y. We're not transforming over y, and so it doesn't really affect the transform at all. Another way of thinking about it, it's like how when we were doing the FFT solution, the left-hand side of that was always the easy one. You can just change the order of the derivative in the integral, and then you just basically get what you started with, right? And so here we get nu times d squared dy squared of f of y. Okay. Okay. Now we have to transform the boundary conditions, just like before. Okay, so to do that, here were the boundary conditions, BC1 and BC2, and again, we don't worry about the initial condition here. Okay, so let's go ahead and take the transform of this condition right here. This condition is that Vx is equal to u cosine omega t. Again, we can just go into our table and look up what the Fourier transform of this actually is. The Fourier transform of a cosine looks like this complicated junk right here. Cosine omega t, so t instead of x, so we can just make that substitution. A instead of omega, okay, and then b here is just equal to 0. And so we get pi times delta of k minus omega plus delta k plus omega. Okay. So BC1 is that f at y equals 0 as a function of k is equal to pi times u is that constant in front, right? Times delta of k minus omega plus delta of k plus omega. Okay. All right. BC2 is that v of x is equal to 0 at y as y goes to infinity. That Fourier transform of 0 is just equal to 0. Okay, so what this basically says is f as y goes to infinity has to equal 0. Our final function has to asymptotically approach 0 as y goes to infinity. Okay, and now step 4 is we have to solve. Notice how the Fourier transform actually turned our PDE into an ODE. Okay, that's kind of a cool thing because remember this left-hand side was df dt. It was a derivative with respect to time, and now the Fourier transform instead turned it into an algebraic expression, turned it into ik times this. Okay, and so now we have an ODE that we can solve. Let me just summarize that ODE right now. Okay, and so we need to solve that ODE. It's a complex ordinary differential equation, but it doesn't really matter. You can just think about I here as if it's the square root of negative. It's just a constant, okay? It does add a lot of weird subtleties that we'll get into once we actually start to look at the solution in detail. Does anyone know what the solution of this differential equation would be?
E to the ikx plus e to the negative ikx.
Something like that. You're getting one step ahead and then getting it wrong, but that's okay. But you sort of have the right idea here. The solution is exponentials, basically, right? If this were a plus in the middle here, then you might try sines and cosines, but instead here we can try exponentials. And the way to formally do this, if we were in sophomore year of college or something like that, and you wanted to actually calculate the solutions to these equations, the way to do this is you substitute in an exponential and figure out what the prefactor of that exponential would be, right? Does it sound familiar? If this doesn't sound familiar, let me just write down a few things that might jog your memory. This is a second order linear ODE. Okay, so we're going to attempt a solution that looks like this. E to the lambda y. Okay, and then we're going to try and figure out what our lambda actually is. Does this sound familiar at all? You get something called a characteristic polynomial, and then you solve for that polynomial. Or you solve that polynomial for what lambda is going to be. Okay, sound familiar at all? I'm going to plug this guy into here. Okay, and so two derivatives of this exponential looks like this. And then one derivative looks something like this. And then we solve for lambda. Okay, the way that we can solve for lambda is we realize that there's an e to the lambda y in both terms, and so we can cancel that out. And so we get lambda squared equals ik over nu, right? And that implies then that lambda is equal to plus or minus the square root of ik over nu. Okay. And so then the actual solution is going to be f of yk is equal to a times e to the plus lambda y plus b times e to the negative lambda y, and then the game is going to be to solve for a and b, right? Before I write that general solution down though, this is where the subtleties of this I comes in, right? The square root of ik over nu, k is a real number. Nu is also a real number, that's just the kinematic viscosity, okay? Does anyone know what I is? what the square root of I is? Someone chatting here. Someone said, Kun Han says negative I? No, that's not true. The square root of I is not negative I
-1,
because,
right? It's -1, right?
No, because the square root of, if you take a square root of something and then you take the square of it, you should get what you started originally, right? The square of -1 is equal to 1. The square of negative I is also equal to -1, right? The square root of I is actually plus or minus 1 over the square root of 2 times 1 plus I. Okay. It's kind of weird. I'll just in the margin real quick maybe show you guys that this is true. Okay, let's just take one of these. 1 over the square root of 2 times 1 plus I times 1 over the square root of 2 times 1 plus I. Okay, let me just multiply this out real quick for you guys. Okay, this is equal to, so I have a 1/2 in the front, and I have to multiply everything together, right? So 1 times 1 is equal to 1. Okay, 1 times I is equal to I. Okay, I times 1 is equal to I. And I times I is equal to -1. So this is equal to I. Okay. If someone wants to ask me later on, maybe at the end of class, how I just randomly pulled the 1 over square root of 2 times 1 plus I out of my butt, and I'll explain to you how that actually comes about. Okay. But for now, let's go ahead and move on. What this implies then is that lambda is equal to plus or minus square root of k over 2 nu times 1 plus I. And so our solution, the general solution, is a times e to the y times the square root of k over 2 nu 1 plus I plus b times negative y 1 plus I, like that. Okay. And just like before, we have to figure out what A and B are in terms of boundary conditions, right? Does this general solution method for this ordinary differential equation sound familiar to you guys? You get two potential solutions, and then you know that your solution has to be a linear combination of those. Just like how previously we would have our solution is equal to A times cosine omega t plus B cosine omega plus B times sine, and then we have to figure out what A and B are and stuff like that, right? That's essentially what we're going to try and do here. We're going to figure out what A and B are in terms of using our two boundary conditions, right? So let me remind you what our boundary conditions are, okay? So our boundary condition was first that f of y equals 0 as a function of k, which in this case is equal to, well, we can plug in a y equals 0 right here, and so this just becomes 1. And this also becomes 1. So we have a plus b has to be equal to whatever we had previously. And let me just write down what we had previously. Okay. And then our boundary condition 2 is basically that f as y goes to infinity. I don't know why my pen just crapped out there. When y goes to infinity as a function of k has to equal 0. So in other words, we have to have a decaying exponential. So exponential must decay as y goes to infinity. Okay. what that means is that if I have an exponential, like for instance, e to the 2y does not work, right? Because as y goes to infinity, that blows up, right? The coefficient in front of my variable in the exponential has to be negative. E to the negative 2y totally works, right? That could satisfy this boundary condition. Does that kind of physically make sense to you guys? Okay. All right. And so what this means is that the coefficient inside exponential must be negative. Just to give you an example, for instance, in these in this term right here, right? In a term like this, you could imagine that this term wouldn't actually work. This would not satisfy boundary condition 2, right? Because the coefficient here in front of the y is positive. It's like e to the 2y. Okay, and so when y goes to infinity, then this guy here blows up. Okay, whereas this term you might expect actually could work because there's a negative here, right? Specifically what I mean is that the coefficient inside the exponential must be negative. It's actually the real coefficient that actually matters, right? Because when I look at a term like this, let me just write out this first term, for instance, over here on the margin. E to the y times, let's say, 1 plus I, that's actually equal to e to the y times e to the iy, right? And this second piece right here, you guys see how these two expressions here are equal, right? The second piece right here is just sinusoidal with respect to y, right? This is just cosine of y plus I sine of y or something like that. And so what actually matters is this coefficient, right? Is this guy right here. And because this guy does not go to 0 as y goes to infinity, then this term would not work, for instance. Okay. Now it's a little tricky if we stare at this guy for a little bit, because k could potentially be negative. Y can't be negative because in our original formulation up here, we're only talking about what happens when the fluid is above the plate, right? But our k, we never said anything. For instance, our integrals right here in terms of k goes from negative infinity to infinity. Our k could potentially be negative. Okay, so that gets a little confusing. So basically, we need to find some sort of value of a and b such that our solution here actually approaches 0 when y goes to infinity. Okay. We need to find a and b such that BC1 and BC2 are satisfied. In other words, a and b have to add together to give you this expression. And the final solution over here has to actually approach 0 when y goes to infinity. Now, because we know that a plus b has to equal this, you might expect that maybe a could equal this term and b could equal this term or something like that, right? That might be one potential guess. Let's actually see what happens if we do that. Okay, let's try. A is equal to pi u delta k minus omega. And b is equal to pi u delta k plus omega. Okay. If we do that, then a times e to the y square root of k over 2 nu times 1 plus I, that's equal to pi u delta k minus omega e to the y square root of k over 2 omega 1 plus I. Okay. And we can actually simplify this a little bit. This term right here is equal to that. Or I just replace this k with an omega. That's the sifting property of delta functions, right? You can think about it as this function right here is a function of k, and so only one value of that function could ever be non-zero. That's when k is equal to omega, and so that's just when k is equal to omega. Okay. The reason why I would do that is because this guy right here, if you look inside this square root, omega is a positive number. That's a frequency, right? Nu is a positive number. And so this guy in front of this, and so what we have here is e to the positive number times y. And e to the positive number times y, for the same reason that we talked about over here, the real coefficient in front of this y is equal to is not correct. Then this can't be right, because this does not decay as y goes to infinity.
Is the 1 plus I still in the exponential on the bottom?
Yes, I apologize. Okay. Okay, so this blows up as y goes to infinity. Okay, just for good measure, we can try the other one as well. I'm going to make this a little bit bigger. These things are getting too small. That is the second term, right? That's equal to pi u delta of k plus omega times e to the minus y square root of k over 2 omega 1 plus I, like that. Okay, and so this is equal to right? Same logic as before, sifting property, right? This delta function is only equal to something that's non-zero when k is equal to negative w or negative omega, and so we can just replace the k with a negative omega. And so this is same thing in front, e to the minus I y times the square root of omega over 2 nu 1 plus I, because the square root of negative 1 is I. And I can multiply this I out, and I get times I plus 1. Sorry, negative I plus 1. See that? I'm just distributing the negative I in here. Okay, and again, the real coefficient here is positive, and so this guy blows up. As y goes to infinity. Okay, hopefully I've been able to convince you so far that we cannot have A be this thing and B be this thing. Okay, so let's try the other case. Okay, if that's the case, then this first term is equal to, I'll just say first term, is equal to pi u delta k plus omega e to the y square root of k over 2 nu 1 plus I. Okay. And this is equal to pi u delta k plus omega. And again, I can replace the k with a negative omega now. Okay, and this is equal to, again, pi u delta k plus omega e to the iy square root of omega over 2 nu 1 plus I. And therefore, this is equal to that, right? Where I just distributed the I now. I times 1 is equal to I, and I times I is equal to negative 1. Now, does this term, what happens to this term when y goes to infinity?
Becomes really small.
It becomes really small, right? Because this is just, the value of this exponential is just e to the negative y times the square root of omega over 2 nu, which is a positive, times something, something, something in terms iy, which is sinusoidal, so we don't need to worry about that, right? So the real coefficient here is negative, and so the value of this exponential becomes really small when y goes to infinity. Okay, and by the same logic, the second term works out too. I don't have enough time. I'm starting to run into the end of the class period. It's the same logic for the second term. Same, especially because I can't write. Same logic for the second term. Also goes to 0. As y goes to, wow, I'm terrible at writing, as y goes to infinity. Okay, and so what that means then is that a is equal to pi u delta k plus omega, and b is equal to this. So the overall solution looks like this. Okay, this term comes from this. This is the first term. Okay, right, pi u delta k plus omega e to the, I just pulled out a negative in the front here to make it even clearer that the y actually goes, the real coefficient is actually negative here. And the second term, again, I didn't have a chance to actually to actually go through, but the logic is essentially the same. It looks like this. Okay. I'm gonna, just for good measure, I'm gonna let, or just for simplicity's sake, I'm gonna let b be written as that. Okay. And so then one way to simplify this whole expression right here is to pull out an e to the minus by. maybe you guys can kind of see how everything kind of falls out. This term I can spread out into an e to the minus by times e to the plus I by. And this one similarly, and I'm just factoring out an e to the minus by. Okay, that's our overall solution. Now, of course, we don't care about the Fourier transformed solution. We care about the original solution, right? We have to take an inverse Fourier transform of this, right? And so we need the original solution, Vx of y and t. And the way we do that then is we take an inverse Fourier transform of this. So we look at our table. Let me go there. We look at our table. And there it is. See that term in terms of cosine? Right? Where A is equal to omega and by is just the b here. Right? You can kind of see that. We actually use this to do the Fourier transform to transform a boundary condition, and it's kind of cool that we were able to basically recover what we originally used to do the Fourier transform. Okay, so what that implies then is that Vx of y and t is equal to whatever we had in the front here, that's fine, u times e to the minus by, but then this guy right here is equal to cosine of omega, because omega is equal to a, t minus by. Okay. That's a super, super nice and neat expression. It's really cool that we were able to get that. I always thought it was really cool. It's kind of a sort of a complicated, although if you think about it, we didn't really do all that. The math wasn't really that complicated. All we did was just solve a second order differential equation. Okay. Is that a rubber band? What are you doing? Okay, sorry. Okay, we didn't, the math wasn't really that complicated. We just had to make sure we were doing our bookkeeping right, and we needed to make sure that we do that we deal with some subtleties with the square root of -1 and I and stuff like that. But all we basically did was just solve this second order differential equation. And it was just a little hairy to actually satisfy these two boundary conditions and make sure that the exponential actually goes to 0 as y goes to infinity. But that's okay. Okay, but we got there. And then all we had to do then was take an inverse Fourier transform. So in other words, just look in the table and then figure out what the solution is going to be. And this is what the solution is. Here's what the solution means physically. Okay. Here's our original plate. Okay. At any given moment in time, the velocity profile looks something like this. Okay, kind of oscillates back and forth. And it has a little bit of a wavelength, if you will, right? The wavelength of these oscillations is just 1 over b, or actually it's 2 pi over b, right? You guys have like maybe taken a class on oscillations or something like that, right? The wavelength is just 2 pi over b. And we have oscillations that essentially damp out as y increases. Okay, this satisfies our boundary condition, right? That our velocity should essentially go to 0 when we get farther and farther away from the plate. Okay, so we have oscillations that damp with increasing y. Okay. The length scale of this damping and the wavelength of the oscillations is 1 over b, which you could write square root of 2 nu over omega. Okay. And then of course the phase of the oscillations is a little bit different depending on where you are in the fluid as well. You can imagine that, you know, if you're somewhere right here, then the plate could be moving like this, and you know the fluid near you is going to be moving slightly out of phase with that same wave, same, you know, frequency and stuff, but it's the phase is going to be slightly different. Okay. Phase changes as y increases. And that just makes physical sense to you, to everyone, hopefully, right? The farther, like when you're not exactly at the fluid, then you know the effect of the oscillations is going to take some time to reach you. It's like waves on an ocean, if you will, right? Okay, and that's the overall solution. Any questions? Okay, hopefully you guys learned a lot today. First time maybe you've actually dealt with complex numbers, not out like, you know, outside of just, hey, I is equal to the square root of -1, right? But in an actual engineering problem. I'm going to take like a 2-minute break where I'm going to get a glass of water and stuff like that, but I'll stay on the call. I'll stop recording at this point, but then like I mentioned for office hours, I will do the normal, like, you know, answer any questions, stuff like that, but I also have an example that I can go over. Okay.
Can that be recorded possibly? Or
Sure,
is-
I'll resume recording at that point.
Thank
Okay.
you so much.
All right, cool.